Hello, my name is Mark, and today we're going to be talking about the constant speed prop, and this is for course AVIA 327 at Liberty University. In particular, we're going to be talking about the constant speed prop on the Piper Seminole PA 44, which I will be shortly taking my check ride in for my multi-engine rating and commercial certificate. So the functions of the prop is something that I need to know and need to be able to explain in detail. So just a quick overview of the Piper Seminole engine. It is direct driven, 180 horsepower, 4-cylinder Lycomine, horizontally opposed, naturally aspirated, and air cooled. Much like the Warriors and Cherokees and Archers, only the Seminole has 2 of them, and of course the horsepower may vary. The big difference between the planes I just talked about versus the Piper Seminole is, take the Archer. It has a fixed pitch prop, which means that what you see is what you get. Your prop stays at the angle that it's at. You can acquire different props. You can get climb props, cruise props, but once you put it on the aircraft, that angle is what you got. Whereas with the Seminole, we have the constant speed prop, which is basically utilizes engine oil to keep the prop angle in an area which the RPMs will remain the same for any given condition that the airplane is in. You can tell quickly if your aircraft has a constant speed prop by the additional control lever found in between the throttle and the mixture levers, and they're typically blue. So the constant speed prop, as discussed, will keep the propeller and an angle of attack for which it will remain constant in its RPMs, whether you are in a climb or a descent, or you have power reduced or pushed forward. Again, we have the blade that you can go into higher pitch or a lower pitch, and then we have a feathered position as well. What we see here is the diagram of how the prop basically works. You have the prop control, which is the blue lever as discussed, and that's how the pilot sets the RPM that's desired. The prop control utilizes a speeder spring, and that manipulates the pilot valve, which either allows oil in or pushes oil out, and controls the angle of the prop. And we also have the flyweights, and then the forces that act against the prop in more of a natural position, shall we call it. And we'll talk about that here in a moment. So it's important to state that in a non-operational, if the engine is not operating, it wants to go back towards the feather position, which you can see here where the blade angles kind of act into the relative wind, where it's going to reduce drag. And you can see the unfeathered here where you have your angle of attack back. So in its natural position, as I said, the prop blade wants to stay at a high angle of attack, or more towards the feathered position, and that's done by 3 forces that act upon the blades while the engine's running. Number 1, we have counterweights that are actually on the prop blades themselves, and those work to push the blade using centrifugal force back into that high angle of attack. We also have this prop spring, which is pushing against the prop and pushing against the oil that's being pumped into the prop hub by the engine. And then third force is in the very tip of the hub, which actually aids the spring. It's actually a nitrogen gas that's charged to about 40 psi, and those 3 forces push the prop into a natural, we'll call it a natural position of a high angle of attack. So just the opposite, when we actually want to, we need a less angle of attack, possibly to get a higher RPM. We see that we have oil pressure coming into the prop hub, that oil pressure is the one force that acts to push the prop into a low angle of attack, which will speed it up and give you a higher RPM. And that oil comes from the engine itself, and he actually utilizes the engine oil pressure. So a drop in oil pressure in your engine means a less effective constant speed prop. So what happens is that speeder spring manipulates the pilot valve, and the pilot valve will either open or close. And when it opens, it can let oil into the hub, which pushes the prop into that lower angle of attack, or it can open towards the oil sump side, and the oil will get pushed out of the hub using the three forces discussed earlier and push it back into the oil in the engine. So there's three conditions that is important to note when you're talking about a constant speed prop: on speed, over speed, under speed. So we have the pilot control, which we set the RPM which is desired, and that manipulates the speeder spring, which manipulates the pilot valve. Well, once that's set, we rely on the flyweights, which we can see here in the top left picture, and also an actual picture on the bottom right. And those flyweights also control the speeder spring. So when you're on speed, or when your RPM is actually at the position of which you want it, the flyweights will be equal, and it will not move that pilot valve, and thus the oil pressure that's inside the prop hub pushing against the other three forces are equal, and everything's happy. In an overspeed condition, you could think of it as your aircraft is in a dive and the wind is hitting the prop and it's spinning the prop faster. The flyweights will open outwards, which will actually pull the speeder spring up and open the pitot valve, and that will cause the oil to move back into the engine sump, and that angle of attack of the blades will increase, thus slowing the RPM back down to what the pilot control valve had been set to. The underspeed condition is the exact opposite. So let's say you were in a climb, the flyweights will slow down due to the centrifugal force and or lack thereof, and that will manipulate the speeder spring and the pilot valve, and will actually allow the engine to push the oil back into the prop hub and move the props into a less angle of attack, allowing them to spin faster, again allowing the RPMs to remain the same as what the pilot control valve had been set to. So that's pretty much the gist of the constant speed prop. It's pretty simple. There are a couple additional facts that you need to know about if you're flying with a constant speed prop. And as I discussed earlier, what we're calling the natural position of the prop is towards the feather position, meaning with all those three forces working on the prop, if you shut the engine down, that prop will want to go into a feathered position. That's great if you have an engine out scenario while you're flying, again to reduce the drag of the non-moving prop. But on the ground, that can cause a problem when it comes to starting the engine. It's really hard on the starter to try to start an engine that's in a full feathered position. So at around 950 RPM, the prop locks will come out, and there's these locks that will keep the prop from feathering and will actually limit it to how high of an attack that it can actually go to. So when in the air and facing a engine out, you want to make sure that you do your checklist and your flows and get that prop feathered if needed before you reduce below 950 RPMs. Another additional fact is when the prop is feathered, obviously the engine shuts down, it's no longer running, so how are you going to get oil pressure into the prop? Well, if we need to restart the engine in air, and we need to get the prop from the unfeathered position, then we have a prop actuator, which is found near the firewall in the engine compartment, and that is filled with oil and remains filled with oil, and it has an additional charge of nitrogen of about 90 psi. So when you pull the prop out of the feathered position, it will actually that nitrogen will push the oil into the engine hub, forcing the blades out of the feathered position, for which then they can catch the air and windmill, hopefully back to a start. If it doesn't start right away, you can always use your starter, and your engine will start back up, and once again rely back on the oil pressure built by the engine, and then the actuator will recharge itself. So that is the constant speed prop. Any questions? I didn't think so. I hope you enjoyed this presentation. Thank you.